Hello, and welcome to day 3 of reInvent. These lights are really bright. Is everybody having a good time? And I hope learning lots. This session is on architectures for high-performance computing, high-throughput computing workloads. My name is Linda Hedges. I'm an HPC specialist. I'm also talking with Professor Modesta from the University of Washington. She's going to present a neuroimaging case study. I assume that you can hear me? Sir? And you want to? Okay. Yeah. This is us. I'm here on the right. My background is from the aerospace community, where I ran computational fluid dynamics simulations for 25 years. So I run on-premise clusters, Cray computers, supercomputers, mainframes, Beowulf clusters, and for the last 8 years, I've run CFD calculations on AWS, and it's my favorite place to run CFD or HPC calculations. Professor Modesta, who's on the left here, is with the Integrated Brain Imaging Center. This back here is the third brain. We were there at her office when we took the picture. And she explores the quantitative changes of functional networks of brains for the search of Parkinson's disease. The talk today, I'm going to start with an introduction on why you would want to use AWS for HPC workloads. Then I'm going to talk about the bulk of the talk, which is potential architectures for your HPC workloads. Professor Modesta is going to talk about her neuroimaging case study. And finally, I'm going to wrap up with some of the most commonly asked questions about HPC on AWS. I also like to call this the myth-busting section. Oh, so to start, what is HPC? At AWS, we define two main categories of HPC workloads. There's high-throughput computing workloads, and then the tightly coupled traditional HPC workloads. The high-throughput computing workloads, this is where you want to run 10,000 or maybe 1 million different iterations of perhaps a Monte Carlo calculation. Each iteration of this calculation can run independently of the others. You can run in any order on any process. And they're also called embarrassingly parallel, pleasingly parallel, and grid computing. For the tightly coupled high-performance computing, every iteration runs lockstep with the next processors run lockstep with each other. And therefore, if you lose one process, you lose the entire calculation. These are much more demanding calculations. The big differentiator between these two workloads is that the high-throughput computing workloads run on just one node. They don't communicate across the network. Sometimes they use OpenMP, so you can run many cores on one instance type. But with the high-performance computing, you're running on often thousands and more instances all running together. Why use AWS for HPC? First of all, you have an unlimited number of architectural options. Starting with the operating system, we're getting a lot of demand for Ubuntu clusters lately. Scientists like Ubuntu, and they want to run Ubuntu clusters. So unlike an on-premise cluster, you can choose the operating system that you want for your workload. And then there are a variety of other architectural options that you get to choose. You can pick the instance type that's best for your workload. It's not one size fits all. You can define the memory that you want. You don't have to pay for extra memory. If you need a high-performance storage system, you can pick that. If you don't have to pay for it. An unlimited number of architectural options. You also have an unlimited number of deployment options. You can submit your job from the console. Perhaps you just have one workload you need to run once. Or you can run an end-to-end automation using a SDK in Java or Python, Ruby, lots of other languages. Lots of HPC developers, they'd like to simply deploy a bash script from their desktop and to use Amazon's CLI to be able to just, with a 100-line script, deploy a cluster automatically and to run a workload. And then, of course, we have CloudFormation for launching very detailed, comprehensive clusters all at once in a matter of minutes. With AWS, there are lots of services that you can draw from to enhance your computing experience. You can use Amazon CloudWatch logs. We have customers who pipe their computational fluid dynamics residuals to the log and then alarm if the residuals are blowing up. They can get a text message or an email to let them know that their calculation needs some attention. Or you can set up to send yourself an email at the end of your computation or when your cluster has launched. We have DynamoDB for storing metadata. We have Glacier for archiving data. And lots of services, machine learning to help you enhance your HPC workload processing. This is the list of my favorite aspects of AWS for running on HPC. First of all, you can experiment without fear. If you've ever begged the system administrator for root privileges and then accidentally bricked the server 3 days later, I don't know if anybody else has done that here. It's extremely humiliating. Then it takes 2 days to put the cluster back together again. With AWS, if you brick it by accident, you do something stupid, you can just terminate the instance, go to your last AMI backup, and continue where you left off. You can experiment with new libraries, different operating systems. You can try a new solver that you haven't tried before. Maybe there's some free software out there on GitHub that you're a little bit worried about. Deploy it to the instance, test it out. If you like it, keep using it. If you don't, you can terminate your instance. You can start and stop instances. This is nice when you're building up a capability. Perhaps you're installing software. It's been a long day. You need to launch a big run. Then the end of the day comes, you're not ready to launch it, you're worried that there's a bug. Stop the instance, you stop paying for it, come back the next morning, turn it on, check it out, launch your big cluster, only pay for what you use. And then, of course, there's spot pricing. With spot pricing, you bid on unused capacity. Spot and HPC are like a match made in heaven. HPC loads are bursty. They're often naturally checkpointed. You need to get on the instance or instances, burst your workload, get the data, and then maybe take 2 weeks to process it. So spot pricing is great for those sorts of workloads. We've recently announced, I think it was yesterday, that with Spot, your instances no longer terminate if you don't want them to terminate, but they can be stopped and then automatically resume when the pricing comes back down and meets your bid price. And this is even better for HPC workloads. And finally, we have continuous updates of the services. We just released C5, which is the latest generation of compute instance. We're always working on our network and making it better, and we continually release new storage options. Unlike with your on-premise cluster, you don't wait 3 or 4 years for your cluster to get old enough that you can redeploy a new one. You can use the latest computing hardware as soon as it's released. But with all these options, it can be a challenge to pick the architecture that you want. There are many architectural choices, and in the next few charts, I'm going to show you some of those architectural patterns for HPC workloads, and then to help give you a guide on how to pick the best pattern for your workload. As I said earlier, on AWS, it's not one size fits all. It's not like your on-premise cluster where you take what they give you. You get to choose. And these architectural choices depend not just on the characteristics of your application, how much memory it uses or how much I/O it has, but also on the desired user experience. Are you putting together a capability for interns and you don't have time to train them in how to use AWS? Or are you deploying an HPC capability? Perhaps you're the analyst and you need to create a capability for the designers who don't want to learn how to create an input file and submit a job. Then you can automate HPC deployment end-to-end, start to finish, launch it from your desktop. So the deployment method, the desired user experience, and then the characteristics of the application go into how you choose your architecture. When choosing an architecture, I usually start in this order here. So I start here with the network. What are the latency and bandwidth requirements? The two distinct categories, high throughput computing, high performance computing. This will give you a sense of which instance you have to choose and which services you will need to use in order to run your cases. After the network, then the next consideration are the storage requirements. Do you need that high-speed file system? Most people think they need the high-speed file system, and most HPC cases actually don't. So it's important to experiment at this step and to figure out what your storage requirements really are. Then pick an instance that matches both those storage requirements and then also the network and latency requirements. At this step where you're picking the network largely comes down to how much memory do you need. Currently, the C4.8x large instance is an amazing instance for HPC workloads. We just, of course, released C5. And the memory to core requirements on that is about 4 gigabytes per core, which is great for most HPC applications. If you need more memory than that, look at the M4, M5 was just announced, and pick your instance type. Finally, you're going to choose your cluster deployment pattern. We divide these cluster deployment patterns into both traditional and cloud-native clusters. I'm going to talk first about traditional clusters, and then I'll talk about cloud-native clusters. Traditional clusters are those where you have a launch pad, you get on, you have a queue and a scheduler, you submit jobs. With an auto-scaling queue, they'll deploy right away. The traditional clusters, and many customers prefer traditional clusters as the first step of the onboarding of their HPC applications into the cloud. This is the architecture for CFN Cluster. CFN Cluster is an open source software package developed by AWS, made available, it's maintained by AWS. There's a URL here which shows the location of a tutorial where you can try CFN Cluster. It will show you how to download it, where the documentation is. It's a quick tutorial, takes about an hour, lets you deploy a hello world, simple MPI application with a queue subfile and into the queue. For the cluster, CFN Cluster is downloaded to your desktop. There's a config file where you can add a placement group, choose your instance type. You then deploy CFN Cluster with a simple command, creates a CloudFormation template that it automatically loads into AWS, and your cluster is created in about 15 minutes, ready for you to use. A master instance is created, which has schedulers. You can choose from SGE, Torque, and Slurm. There's some other middleware on there, compilers, Ganglia, if you want to inspect your entire cluster. Python's installed automatically. And as you submit a job into your queue, Amazon CloudWatch is watching that queue and spins up your compute nodes to handle the compute capacity that you've requested. And it will auto-scale your compute fleet to as big as you allow it. So even though you're submitting through a scheduler, you should never have to actually wait in the queue for your job to run. An NFS shared EBS volume is automatically set up and shared to your compute nodes. You can pre-install software on your volume. You can save that off as a snapshot. And then you can launch an unlimited number of these clusters based off the snapshot. The cluster is automatically provisioned with your software. We run CFN Cluster with ANSYS Fluent, Star CCM, WRF, lots of tightly coupled and lots of high throughput computing applications. 2 years ago acquired NICE, which is a HPC company with 20 years of experience. They're very well known for NICE DCV, which is the premier remote visualization package. EngineFrame offers a portal experience for deploying workloads on the cloud. Many customers already use EngineFrame on-premise. Now you can use EngineFrame in the cloud. This URL here points to the tutorial location. It lets you get started, helps you launch an example cluster, get some experience with EngineFrame. EngineFrame is set up for an easy user portal experience. You can log in through Active Directory. A system administrator can maintain the services. They set up a variety of different workloads through the system administrator console. Users can then get on and use the services that they have permission to use. ANSYS Flight is another cluster experience that's available in the marketplace. There are two versions. There's a free version in the marketplace, and then there's a supported version. It comes pre-installed with lots of scientific software, libraries, and compilers already. You get access to LAMPS or OpenFOAM, GROMACS through a checkout capability. It also provisions a web SSH interface and offers an auto-scaling cluster experience. A cloudy cluster has recently been in the news. I don't know if you saw, but Clemson University ran a 1.1 million vCPU cluster based on cloudy cluster. You can get access to cloudy cluster in the marketplace. Cloudy cluster gives you the ability to provision with a high-speed file system, EBS volumes, EFS, or off of S3. It also comes packaged with a variety of software packages, including WRF, OpenFOAM, LAMPS, and GROMACS. It's a very powerful package. They were able to run a 1.1 million vCPU cluster using spot instances. The cluster was up for 18 hours to manage their high-throughput computing workload. And then for a completely turnkey solution, you can turn to one of our partners, Rescale. Rescale will provide a completely managed capability running out of your account. They provide, in particular, access to licensed software. If you're having troubles getting licenses with some of these organizations, they will help you navigate licensing concerns. Once people have tried a traditional cluster approach, they often turn to a cloud-native approach. Cloud-native approach gives you further ability to optimize on performance and on cost in particular. Cloud-native is when you're using services available on AWS that are not typically available on premise. Maybe you store most of your data in S3 where it's cheaper to store your data, or you use DynamoDB to store the metadata about cases that you can poll to find out when you ran a case, how long that case took, or what case that you ran. Using AWS Lambda, you can deploy your cases entirely serverless, or use Lambda to deploy instances as you need them for your computation. API Gateway is often used by HPC customers that are looking to provide services for other customers or perhaps other organizations. Here's the simplest of cloud-native configurations. You drop an input file into an S3 bucket. It triggers Lambda. If your computation is 5 minutes or less, performs the calculation, creates an output file. That then gets dropped in an output file bucket. Maybe you look at all these files with QuickSight, or you then carry it on to the next step of your processing. Here's a more complicated cloud-native architecture. It's very common. Start again with an input file, drop it into an S3 bucket. Amazon Lambda triggers, AWS Lambda triggers, and it starts up a cluster for you, or it checks to see if the cluster exists and deploys the case to SQS. SQS then maintains, in this case, an ECS Docker cluster based on Spot. I heard today that we have new container services that might also work in this model. While SQS is deploying those cases to the container service, it is also via Lambda keeping the autoscaler aware of how big that cluster needs to be for the workloads that are being deployed. Once the data is processed, it then drops that data into an output file, where then more analysis can be performed. This portion here in the green box is something that happens quite frequently with high throughput computing workloads, which is why AWS Batch was announced last year at reInvent. So AWS Batch has been very popular with the high throughput computing community. It fully sets up your infrastructure. It will choose the best instance type for your workload if you want. It will manage Spot. And it's a fully managed scheduler. Yesterday, they announced that it also now handles array parameters. So if you have a Monte Carlo simulation with one code, but an input file which changes in different parametric ways, you can launch fully 10,000 cases with just one call of the API. Next, Professor Modesta is here to talk about her journey to cloud on the neuroimaging case study.
Thank you, Linda. Hi, I work at the University of Washington doing neuroimaging research at the Integrated Brain Imaging Center. And I use primarily magnetic resonance imaging, or MRI. MRI uses magnetic fields and radio frequency pulses to excite the hydrogen atoms in the water molecules in the brain, emitting a signal that we can then use to create images of the brain. So people are probably most familiar with images such as the anatomical images. Here, if you can see, this doesn't show very well. There. So at the top here, you can see the structure of the brain is very well delineated. You can see the gray matter and the white matter, subcortical structures, if there's a tumor, things like that. And we use those images, as I'll show you, in our processing pipelines. But we can also do more sophisticated things with neuroimaging, such as diffusion imaging, as shown below here. And what we do in this way is we obtain a measurement of the diffusion direction of water molecules through the brain. And so when we obtain their diffusion in different directions, we can combine all of this information to obtain a structural map of the white matter of the brain, which gives us a map of how the brain is connected. Once we get these images, we do a lot of processing to them, and this is where computation is so important. This is an example of one of the pipelines that we use quite a lot. This is called Freesurfer. It comes from Harvard MGH. And it's a commonly used pipeline that processes structural images, first by removing the non-brain structures, a process called skull stripping, but then by delineating the gray-white matter boundary, obtaining a measurement of what's called cortical thickness, the thickness of the cortex all throughout the brain. It can also obtain volume measurements of subcortical structures and identify the folds in the brain so that we can align different people and thus compare the thickness of the cortex in different areas. This is really important because this is one of the few measurements that we have of looking sensitively at the thickness of the cortex in people who are alive. And it tells us a lot about, for example, childhood development. For a long time, the cortex gets thicker in childhood development, and then it thins again as connections are pruned. This is a normal stage of development, but in children who have developmental disorders, this is altered. Either the peak of thickness or the slope of change is altered. And so this is something that tells us about how developmental diseases progress. The other thing that I'm particularly interested in looking at is neurodegenerative disease, where there's basically a loss of gray matter in specific areas of the brain. And we can see this quite well with these kinds of quantitative neuroimaging techniques to look at, for example, what parts of the brain are affected in Alzheimer's and Parkinson's disease, and maybe identify early biomarkers. To give you an example of the workflow for something like the diffusion data that I showed you, this is an example workflow for that called Tractography. What we can do is, on the left hand, this colorful picture is very high resolution data where we've used the direction of the diffusion to create a map of the connectivity of the quote-unquote fibers in the brain. This is obviously not to scale. These fibers are very much smaller than this, but still you can get an idea of the complexity of the graph of the brain. This can be simplified to what you see here on the right-hand side, which is using different regions of interest in the brain and looking at the connection of each of those regions to all others, thus quantifying that strength of connection and making a graph. This is important because network analysis has been frequently used now to look at changes in structural connectivity of the brain and structural organization and how that changes with disease. And also pragmatically, it's nice to know that we might, if a part of the brain is connected in a similar fashion to the areas right next to it, this can be used to delineate functional regions and areas that we can then use to simplify our analysis. So this type of analysis, this tractography analysis, takes approximately 36 hours per brain. But it's completely parallelizable because we can take each of the regions that we're looking at and compute its connections to all others in parallel. So we can distribute this quite well. And in contrast, the Freesurfer example, the structural pipeline, takes about 8 hours. So you can see that it's on the order of large numbers of hours of computation on reasonable workstations. Now, this is the reality of the hardware that we have typically to do analyses. We have desktops that have limited numbers of cores, and we use them not for the heavy-duty processing. We use them primarily for visualization of the results, maybe developing and testing pipelines, but primarily interactive use. For the analysis that we do in a lab, we have, say, a workstation, which might contain 24 to 28 cores, has some sort of amount of storage, and that's typically used to support about one investigator's worth of data and processing. And then when we want to scale beyond that, which I'll explain to you we do, one of the offerings that we have available to us is the University of Washington's HIAC system, which is the high-performance computing cluster. And let's assume that a share of that would be reasonable for about 10 investigators, say, might be 10 times the size of a workstation, so about 10 nodes. And these are the sort of the reference architectures that I'm looking at. Now, the problem is that we are limited in the number of people that we can actually scan and process by the cost of the scans. It's about $600 per hour to do that, and the size of the grants that we can get. So that means that most studies that an individual investigator would do would involve about 50 to 200 subjects. So if you look at what can be done in a reasonable amount of time, and by that I mean like that I don't forget what I was trying to do before when I started it, and I think that this is about a weekend. So you can see that a desktop doesn't do very much, about 8 Freesurfer jobs and 1 tractography job. A workstation is a lot better. It can do, a reasonable number of Freesurfer jobs, but not very much as far as sophisticated analysis such as the tractography. And even a cluster, it looks like it's pretty good for the numbers I described. But the problem is that there's a move in neuroinformatics towards pooling data. So having large amounts of data available from multiple sites, putting that together for analysis. For example, doing things like epidemiological studies, where you image enough people, like hundreds of thousands of people, longitudinally, so that there's some percentage of probability that some number of people will actually develop a disease you're interested in that might be relatively rare. And then you can go back in time to their earlier imaging and see, well, what were the precursors of that disease? Could we see something about how their networks changed that would describe to us, what was going on? So we really want to be able to burst out to that type of large-scale computation, and the kinds of hardware that we are able to get don't help us. And so this is, and I should just highlight, we don't even have the cluster. We have things like these workstations. So we looked at whether it made sense to purchase hardware. Here on the x-axis is utilization. So going from 100% utilization to 0% utilization. And on the y-axis is the cost per core per hour in log scale. So you've got 3 lines here, which on the top it's the cluster, on the middle, the green one, is the workstation line, and the bottom is the desktop line. So what you can see, and then what you can see here is that there's 2 horizontal lines. The bottom one is the cost, because it doesn't vary by utilization, for spot pricing from last June. And the somewhat higher line is the cost for a C4 instance on demand. So 2 things to take away from this. Number 1, the spot pricing is always lower than the cost of our workstation. Number 2, the cost of an on-demand C4 instance is always lower than the cost of the Hayek cluster. So this tells us that it could be very cost-effective to run these workloads, especially since our utilization is very low in general, mostly in the 25 to 0% range. Now, these graphs don't take into account the cost of storage that would up those lines, but because our utilization is so low, we're really looking that we have a lot of headroom in that regard. We wanted to know how much it was going to cost us to run our specific applications. So we set up a benchmarking experiment where we looked specifically at M4 and C4 instances to examine how much it was going to cost to run our types of workloads. So we didn't really have to consider too much, as Linda was describing, the architectural decisions that one might make. Our big decision was what kinds of instances should we choose, because we're not very I/O intensive. All the jobs are independent network-wise. And so what we wanted to know, though, was how data dependent were our execution times. Could we predict how long something was going to take, one brain basically, from taking another reference brain and guessing? And we wanted to know how variable execution time was just even on the same data, because some of our algorithms might not be the same. And we also cared very much that it look as familiar as possible. So we were very attracted to CFN Cluster for this reason. A virtual cluster looks familiar to us, and spot pricing would make things very affordable, especially because all of our workloads are written in a fault-tolerant and reproducible manner, so that if an instance had to stop because it was priced out, then we could pick up where we left off. And now, with spot pricing, you no longer terminate an instance, it stops and then can resume. And what our thinking was that we would generate configurations of machines, of clusters, basically tailored for specific workloads and applications. These are some results from a benchmark for Freesurfer. You probably can't read the axis labels here, but essentially the takeaway here is that the the orange toned bars are for C4 instances, and as you move towards the right-hand side, the instance is larger. And the purple tones are for M4 instances, and again, as you move towards the right, you're looking at a larger instance. The graph on the left is just a standard resolution MR structural image, and the graph on the right is for a high resolution image. So, and on the y-axis you have the price to basically process one brain. So and the scales are different. But the key thing here is we were really surprised that across a whole bunch of different applications, we saw several clear patterns emerge. Number one was that for our applications that we looked at, the C4 instances were cheaper than the M4 instances for the same jobs. And the other thing was that was surprising to us was that the smaller instances within each class were faster or cheaper than the larger instances. And we believe that this is due to the fact that when we're occupying a smaller part of a physical machine, we get the advantages of turbo boosting to speed up that part of the workload. So what we learned here in summary was that AWS can be a lot cheaper than an on-premises cluster. And furthermore, the cost of our CPU-intensive applications, they're all CPU-intensive, was quite predictable. I went over a lot of details here, but they're covered quite a lot in a lot more detail. You can read about all those details, actually, in this paper that we published, which is called Running Neuroimaging Applications on AWS. This is an open access paper in the Frontiers in Neuroinformatics journal. So if you're interested, please do look at that data. That paper only came out a few weeks ago. But it goes through a lot of the things that we did and you know, what we learned. So in the end, the complexity that we had anticipated dealing with in terms of making all of these architectural decisions turned out to not be as complex at all. The C4 instances were the fastest ones. They were good enough memory. and spot pricing seemed to work quite well for us. That said, there were some interesting things. I wrote a supplement for that paper to describe all the steps that a person would have to do in neuroimaging. Take like one of my students, for example, to implement this and run a real cluster, and it was 14 steps. That's a lot of steps. And the thing is that the people who I trained to do this, they're interested in solving those questions about the brain. And so they don't necessarily even come from a programming background. They come from neurobiology, they come from psychology. To do this work, they have to know some amount of programming, some scripting, something of that sort. And that's what I focus on teaching them, in addition to all the neuroimaging parts of the analyses that they need to learn how to do. Those 14 steps to get a cluster started are just additional things that take away from the ability to do science. Everything that they have to learn about technology is something that they take away from science, and especially in retrospect, considering that some of these decisions were so easy, you know, if you don't have to think about it, why even know about it? So it would be very much nicer if we could make those 14 steps into one step, which is basically push a button, you want to run a cluster, it should look a lot like your cluster at home and have the same software, and then you're good. And that would just simplify things a lot and really use AWS, I think, for its greatest power. So with that, I will turn the podium back over to Linda.
Thank you. In this next section, I'm going to talk about some of the most commonly asked questions about HPC on AWS. These are the questions that I'm asked day in and day out. Is AWS secure? Can you really get all the cores that you need to run massively at scale? Is it cost effective? And then finally, probably the most intense question of all, how good is your network? Can I really run a tightly coupled case? Yes, AWS is secure. And today is what, day 3 of reInvent, so I'm sure you've heard lots about security already. It is job 0 for us. And we provide many tools, encryption at rest, encryption at transit, IAM for controlling or offering permissions to your users. Just recently announced a new GovCloud region. Much of HPC workloads requires ITAR compliance. We now have 2 regions for you to run these HPC workloads, one on the East Coast and one on the West Coast. Just a reminder that AWS security is a shared responsibility. AWS is responsible for security from the hypervisor on down. We separate the network, we isolate compute and storage, but users are responsible for controlling their passwords and then also keeping their security groups in check. And in general, the security from the operating system on up. I believe we've also introduced new security tools to make this even easier to do. You can go massively parallel on AWS. Again, a few weeks ago, Clemson University released their 1.1 million processor cluster for high-throughput computing workloads on Spot. That's an amazing number of cores. So yes, high-throughput computing clusters, you can get the really big clusters, but also for tightly coupled HPC workloads, you can get 1,000, 2,000 cores to run these tightly coupled workloads and even more. But what we see a lot of our customers doing who run these tightly coupled workloads is they run these HPC cases in parallel, launching hundreds to even thousands of tightly coupled workloads all at once. One of my favorite examples, I guess with the 1.1 million cluster out, this is kind of old news, but this is an example where Fermilab took CERN data to help search for the Higgs boson particle. This was a couple years ago, and they ran this workload on AWS. They burst into the cloud, they ran on Spot, and they reduced what would have been a 6-week workload down to 10 days to help find the Higgs boson particle. While they were running this, they put out on their website the plot of how many cores that they were using and as a function of time. So you can see down here, this is time, this is over the, I think this is a snapshot of the 10-day period, and then here is the core count. You can see they peaked at 58,000 cores. But what I find particularly interesting is somewhere right here, they go from about 40,000 cores to 0 cores. And one can conjecture a couple of things might have happened, but most likely what happened was that their spot bid price was, they were outbid on the spot market, and this stopped all the instances. So they went from 40,000 instances down to 0. They then waited, I think this is about an hour and a half, and then when the spot price came back down again, all the instances started back up again. They were able to get 50 and 58,000 to complete the workload. AWS is cost effective. There are a variety of models that you can pay for your cluster computing. Important to match the right payment model with the workload. There's on-demand, one low price, but requires no commitments. Reserved instances, if you have daily runs, you know you're going to have these runs, then you can get a 60% discount with a reserved instance. And finally, there's Spot. Spot is just amazing for HPC workloads. A lot of our HPC customers work with it. HPC is bursty. Burst the workloads, take time then to process it. It's perfect for Spot. But with this cost model, you can imagine, say you're doing weather calculations, and perhaps you know you have a daily forecast that you have to do. For that, you might want to use a reserved instance. You know you're going to be running this workload every single day. But perhaps there's a weather issue coming up. Maybe there's a hurricane coming in, and you need to burst your workload. You might choose on demand at that point. You have to burst. You have to run the cases right now, and you can't risk losing them if your spot price is exceeded. But perhaps you're doing climate modeling, and you need to run 100 weather simulations, and if the run completes tomorrow or maybe the next day, it's not so very important, and that's when you can go with spot pricing. TLG Aerospace uses spot pricing exclusively, and by doing this, they were able to achieve a 75% discount for running their HPC workloads over previous cloud providers. TLG Aerospace, again, runs hundreds of these 1,000-core tightly coupled cases at a time. And they've said in a webinar recently, you can find that on the web, that in 1 year of running on Spot, they were only terminated twice. They only lost 2 cases, which more than made up the expense to rerun those cases, was more than made up by the savings by running in general on Spot. Now, if you plan on using Spot with your HPC workloads, you're going to want to use Spot Fleet Advisor to check a particular region, availability zone, and instance type to get a sense of what the likelihood is before you launch your big case. You can also look at the pricing history, see how volatile the region is in the moment. We have some regions that have had 60% discounts on the C4.8x large instance type for over 3 months, as long as the pricing history has been made available. Lots of customers asked about running tightly coupled workloads on AWS. There's a common question, is your network good enough to run these cases? And yes, it is good enough to run most tightly coupled workloads. You can see this is WRF, a very common HPC workload, and here it's being run on over 3,000 cores. We've run WRF on over 4,000 cores. It scales very nicely. These scale-up curves, by the way, have cores here on the x-axis, scale up, which is how many times faster the case is compared to whatever your baseline is. And here's the same scale-up curve for ANSYS Fluent. This case, you can see, is run on over 2,000 cores. It's a big case. It runs well on AWS. ANSYS Fluent runs very well on AWS, but if you have a small case, you're not going to scale to 2,000 cores, but you will scale to hundreds or maybe 1,000 cores. AWS has a fully point-to-point, non-blocking network, which is great for these HPC calculations. The network was designed to run at scale. You're never your own noisy neighbor. We have enhanced networking, which keeps jitter to a minimum. You can imagine that the speed of a tightly coupled calculation is not the speed of the fastest network connection, it's the speed of the slowest network connection. So your calculation can't advance until all processes are done. AWS has very little jitter on the network, and it works really well for these calculations. If you're looking to get started with HPC on AWS, I would recommend starting with the Researcher's Handbook. It can be found at this URL down here where you can download it. It's about 150 pages, and it's written in scientist, engineer speak. It's not written in developer speak, which can make it easier for some audience. It'll teach you how to get started, how to use CFN Cluster, what other options are out there, how to keep from exceeding your budget accidentally. It's very reasonable, talks about lots of marketplace offerings that can help set up your workloads. I also want to give a shout out to 2 recently released white papers that are now available on HPC. We just recently released the well-architected HPC lens. You can download that at our white paper website. And then also recently was a white paper released on EDA workloads, which offers a lot of tips for running in general HPC cases. I like to point people to the Getting Started pages on AWS. Really nice page, little tutorials, 10-minute tutorials. If you're bored at work, you want to get energized, go to the tutorial page and learn something new. Machine learning, or there's one tutorial on how to launch CFN Cluster here. Thank you all for coming to the session, and thank you, Professor Modesta. If you have any questions for either of us, we'd be welcome to ask them right now.